Howdy y'all, so we're going to look at scatterplot and correlation. In the previous video we saw equations of lines and I kind of cliffhangered us into where we were going, which is looking at how two quantitative variables are related. And so that is what a scatterplot can show us. A scatterplot is a type of graph and it plots the points for two quantitative variables. Let's look at an example that illustrates a scatterplot. I'm going to draw a Cartesian coordinate plane, and I've got a particular example in mind. On the vertical axis, I'm going to indicate the number of calories expended or burned, and on the horizontal axis, I'm going to write the time on treadmill, everyone's favorite, in minutes. Now, with these two variables, you would expect a certain type of relationship, right? You would expect that the more time someone spends on the treadmill, the more calories they are expected to burn. For instance, someone who spends a small amount of time on a treadmill is expected to burn a little calories, and someone who spends more time is expected to burn more calories, and it would kind of take on a gradient in between, right? You expect that the more time someone spends, the more calories they would burn. That's not guaranteed, but that's expected. Furthermore, two individuals could spend the same amount of time on a treadmill, but burn a different number of calories. There is variability expected in the measurements of these two variables. And even though they spent the same amount of time, there's going to be variation in the y variable. It could even go the other way around. Two individuals who, say, burned the same number of calories could have spent different amount of times on the treadmill. These two variables are what we would call positively correlated, because as one variable increases, the other variable increases as well. So these two variables have a positive correlation. We are measuring here two variables, and typically those are observed in the same individual, right? One individual gave you two bits of info, the number of minutes and the number of calories. You might put a coordinate here. Maybe this was 10 minutes and they burnt 112 calories. And this is what we would call bivariate data. And as a reminder, we typically graph the response variable on the vertical axis, and on the horizontal axis is where we typically graph or plot the explanatory variable. Where we are headed in the next video is discussing how do we plot a line to this data. If we want to describe the trend or relationship between these two variables, can we use an equation of a line to do so? And so that's where we're going in the next video. But a few more things about correlation. Here, if we had two variables that were positively correlated, they would have a slope that was positive. Let's look at an example that illustrates two variables that have a negative correlation. Two variables that are negatively correlated would have a slope that is negative. And as you were to plot this bivariate data, as x gets large, y would get small. So one is bigger when one is smaller, and vice versa. And if you were to plot this line that fit this data best, it would have a negative slope. Let's look at another example that doesn't have a positive correlation or a negative correlation. Here, let's look at two variables that may have no correlation. I've got a particular example in mind. On the vertical axis, I'm going to write a variable for exam scores on any particular exam, and on the horizontal axis, something that has nothing to do with it, let's say shoe size. Now, these two variables, you don't anticipate to have any influence on each other, right? So regardless of your shoe size, you'd expect a whole range of exam scores. So these two individuals would have high and low exam scores, even though they had the same shoe size. And you would expect that to be the case not only for smaller shoe sizes, but also for larger shoe sizes. So here I'm going to draw a tick mark where two people had the same shoe size, maybe a little larger, but two different exam scores. And you would expect the whole gambit in between, with where this looks kind of just like a splatter. There's no obvious upward trend, no obvious downward trend. If you were to draw a line that best described this data set, you totally could. Just crunch the numbers, I'll show you how to do that. You would probably end up with a horizontal line in which the slope would be about 0. So far we've got some pretty broad categorizations here for correlation. We've got a positive correlation, we've got negative, and then also no linear relationship. And we can actually measure in a quantitative way how correlated two variables are. This is with what is called the linear correlation coefficient. And this is a measure of how strongly two variables are associated, and also the direction of that association. So we've got positive, we've got negative. Sometimes this is called the Pearson linear correlation coefficient. I don't usually call it that, but I think our textbook does sometimes. And something worth mentioning, which I neglected, was that all of these examples are generally applied to quantitative variables, not qualitative. We usually represent the linear correlation coefficient with the letter R, little r, and this has some properties. Little r, the correlation coefficient, can be anywhere between -1 and +1. So it can equal 1, it can equal -1, and positive or negative, that tells you that direction of that correlation. And the in-between values are a little hard to describe, and I'm going to show you some pictures here shortly, but the direction is indicated by either a positive or negative r. We can draw what it looks like when r is negative or +1 for a scatter plot. So let's do that. Suppose r is a +1. Let's see what that looks like. If r was a +1, we would have a perfect linear relationship with our two variables. If we were to draw a line, it would be the absolute perfect line, such that it would go through every single dot without question. So this is an example of when r is +1. It's a perfect linear positive relationship. And in this scenario, if you were to move x over a little bit, you know exactly what to expect and why. that is what makes it a perfect relationship. Let's look at -1 for the linear correlation value. It's a very similar story in which you would just have a negative correlation and all the dots would be in that perfect line, and this line would go through all the dots. So that's what a linear correlation coefficient looks like when R is +1 or -1. Let's look at some examples for in between. Those are kind of hard to draw, so I'm going to look at a couple computer-generated images. Here we've got on the top a scatter plot that says -0.7. So we see a negative relationship between the two variables. And this is what about 0.7 looks like. I want you to imagine the line that would go through or best describe this scatter plot. And imagine just how clumped or not clumped all the data points are around that line. So that's what 0.7 is like. Let's consider this one on the bottom. This shows positive 0.675. And so we see a positive relationship, and there's a little bit more spread in the dots, right? And over here for big X's, there's actually a lot more spread than over here for the small X's, and that's kind of problematic. But overall, we see if there was a line, there's a bit more spread or variability about that line. Now over here with -0.3, this kind of just looks like a splatter, doesn't it? It's hard to see it, but if you were to put a line to it, it would have a negative slope, but it's really hard to make out any overall trends. This is kind of a weak negative correlation between these two variables. On this next example, we've got a really high correlation value here. Imagine the line here and how tightly clumped all those dots are. So this is a very good linear correlation coefficient between these two variables. It's about 0.994. So the best you can get is a 1 or -1. And so this is very close to as good as it gets with 0.994. Let's take a look over here now. This is also a moderately strong correlation between these two variables, in which if I was to imagine the line that best describes this data set, I'm kind of thinking about how tightly clumped those dots are around that line. Now, I want to show you another example that doesn't necessarily demonstrate a positive or a negative relationship. And so here I've started drawing an interesting looking scatter plot in which the y values are going up and down, up and down. It's kind of like a wave, right? You've seen these waves before, maybe in like a geometry. Can you think of a couple variables that might have this kind of behavior? Something that resonates with me is the tides in the ocean. So this could be the sea level height, and this would be over time, right? We have like high tides and low tides throughout the day. And so there's definitely a relationship between these two variables, but it is not a linear relationship. And so therefore, we cannot use the linear correlation coefficient to describe the relationship here. If you were to put a line to it, you'd probably get a line that has a slope of 0, indicating no linear or a non-linear relationship. I want to show you a couple more examples. Here I've got 4 scatter plots and 4 linear correlation values, and I want to see if we can match them up. So if you could, maybe pause the video and see if you can match scatterplot 1, 2, 3, and 4 with the correct correlation value on the left. All right, give it a pause. Here's some of my thought process in looking at this. This first scatterplot does not look linear at all. It looks like a parabola. It would have a linear correlation, therefore near 0. So which one of these is closest to 0? It's that third one. Okay, so that goes with number 1. Now, looking at the next two scatterplots, these both look positively correlated. So I might just hold off on those for a second, because it's the fourth scatterplot on the bottom right that looks like it has a negative correlation. It's the only one that does so. And so there's only one R value that is negative, so that's number 4 goes with A. Now let's get back to these two. Now they both appear positively correlated, but which one of them looks like it's got a more tightly clumped data set? That appears like it's number 2 to me, right? Because if I was to draw this line that best described it, it appears that those dots are like really tied up on that line. And so therefore that's going to have a higher R value. And so I think that's going to match up with D. Therefore, scatterplot 3 must go with B. And if you were to look at the line for scatterplot 3, I think it's clear that there's a lot more spread in scatterplot number 3 than in scatterplot number 2. One more thing that I would like to mention, we had mentioned this in the first couple weeks of our class when we talked about quantitative and categorical variables, is how two variables, just because they may be correlated, it does not mean that they cause a change in one another. Just because two variables may occur with each other, it does not necessarily mean that one causes the other to change. Let's look at some examples here. Here, the website, if you want to look at it, Tyler Vegan, I think I googled Tyler Vegan correlation, and he's got some interesting data sets here that are actually real and happen to have a correlation but have nothing to do with each other. Let's take a look here. We've got the per capita consumption of margarine and correlated with the divorce rate in Maine. Certainly, these don't have anything to do with each other, right? But wow, they are very highly correlated, 99+%. And he's graphed these in a slightly different way than we would have, but this is just to illustrate that two variables may occur with each other and rise and fall with each other, but it does not necessarily imply that if you, for chance, eat more margarine, that's going to put you at a higher risk of divorce. That's definitely not true. Here's another example. The number of people killed by venomous spiders correlated with the number of letters in the winning words for the National Spelling Bee. So again, two variables that you would expect to have no influence upon one another. You do not expect them to have any causative relationship for certain, but they happen to be highly correlated. So I think these are kind of fun to think about, but the moral of the story, correlation does not imply causation. In the next video, we're going to see how do we actually create the line that describes these data sets. And that's with what's called linear regression. See you there.